This is the beginning of the 2.2 lecture on the inverse of a matrix. And I just want to make a note here that for section 2.2 and 2.3, we're only going to be talking about n by n square matrices. And there are several sections in this course where we make that restriction, and I'll try to keep pointing that out. This idea of inverse of a matrix only applies to square matrices. All right, so let's get started here. So let A be an n by n square matrix. A is said to be invertible if there is another n by n matrix that I call C here, such that A times C equals the identity matrix and C times A equals the identity matrix. In such a case, C is called the inverse of A. Now, there's only one possible inverse of A, because suppose there was another matrix B that satisfied the same property, such that AB equals the identity and BA equals the identity. Well, then B is B times the identity matrix, which is B times AC, which we know from above, which is BA times C because of associativity, and then BA is equal to the identity matrix times C, which is equal to C. So this chain of equivalences shows that B would have to equal to C. That means if there is an inverse of a matrix A, it's unique. There's only one. And so from now on, we're going to use a special notation for this. We're going to write the inverse as A to the minus 1 power. And we're going to read that as A inverse. So what's really important here is what's in the box. A inverse times A is the n by n identity matrix, and A times A inverse is also the identity matrix. Now, this notation is analogous to the multiplicative inverses of numbers. Just like, 5 to the negative 1 times 5 is 1, 2 to the negative 1 times 2 is 1. But the use of the minus 1 in A to the minus 1 does not mean 1 over. There's no such thing as 1 over a matrix. It's not defined, it's never defined. That's never going to happen. So it's just, it's like there are some connections with numbers, but not a total connection. It kind of reminds me of when we say an inverse function, right? When we write f to the minus 1, we do not mean 1 over f. Now, we will also see that many n by n matrices do not have an inverse. They are non-invertible. So there are going to be two kinds of square matrices, those that are invertible and those that are not. Matrices that are not invertible are called singular. Invertible matrices are called non-singular. And ever since I was a student, I found this singular, non-singular language confusing. So we're not going to use it. I just mention it here because you may see it elsewhere. But in our course, we'll always just say invertible or non-invertible. So now we get to Theorem 5 of Chapter 2. So our textbook starts renumbering the theorems in each chapter. And why are we already to Theorem 5? Well, if I don't think it's worth making a big deal about a numbered theorem, I don't. So the book had some numbered theorems in the first section that we're not going to number. And yet I'll keep the textbook numbers on the theorems that I include just so we can make the connection with the book. So here we go. Let A be an invertible n by n matrix, and let B be a vector in Rn. So if A is an invertible square matrix, then the equation AX equals B has precisely one solution, has a unique solution given by X equals A inverse times the vector B. Well, this is a really important result, and it's kind of a really straightforward result. All right, let's look at the proof starting on the next page. So again, we're saying if A is n by n invertible, then AX equals B has a unique solution. It has a solution, so you never have an inconsistent system in that case. And it has a unique solution. You never have free variables. You never have infinitely many solutions. So why is this the case? Well, again, given that the matrix A is invertible, take that equation AX equals B, and first of all, what I want to do is just check that X equals A inverse B actually is a solution. So this A inverse B stands for a column vector that you get when you multiply the inverse of A times B. So if we plug A inverse B into that equation, we can rewrite it in this way. A inverse is the identity matrix. The identity matrix times B is B. B equals B, it checks out. Now, can there be another solution to the equation AX equals B? And there can't be. There's only one, because if we take that equation AX equals B and multiply both sides on the left by A inverse, we actually get that X has to equal A inverse B. So that's the only possible solution to that equation. So it's sort of like in this special case where you have an invertible matrix, you can multiply both sides by A inverse. It's kind of like intuitively like dividing by A, even though we're not really dividing. And then you can solve for the X vector. Theorem 6 of chapter 2 are basically some properties of inverse. If A is an invertible matrix, then A inverse is also invertible, and the inverse of the inverse is A. That should kind of seem reasonable. If A and B are both invertible matrices, then A times B is also invertible, and AB inverse is equal to B inverse times A inverse. So that we're kind of saying the inverse of the product is the product of the inverses, but what's surprising here is that we got to reverse the order, and we're going to talk about that for a couple minutes when we look at the proof. And then part C, if A is invertible, then so is A transpose. There's our A transpose notation. And the inverse of the transpose equals the transpose of the inverse. Now, I think we'll talk about the proof of these items. A, you just got to kind of think about, and A makes sense. B, why, if A times B, if A and B are both invertible, why is the inverse of A B inverse A inverse? So all you got to do is take AB, the product, times this B inverse A inverse. When we line up multiplication this way, the B inverse are right next to each other, so they become the identity matrix in the middle of all this. But when you have other matrices times the identity matrix, that gets absorbed, and we're just left with A times A inverse, which is also the identity matrix. And that's exactly what it means for B inverse A inverse to be the inverse of AB. So you can also verify that B inverse A inverse times AB on the other side equals the identity matrix. I didn't write out those steps. I think I'll let you look at part C on your own. Now, the next step is going to be how to find the inverse of a matrix. And we're going to save this for the next video segment. It's a crucial kind of problem for us.